Hello guys, and welcome back to our YouTube channel. Of course, this is the #1 online platform that offers you the best tutorials. And today we are here to introduce differential calculus. And under differential calculus, on this first topic we are going to discuss about functions and graphs. That is, we are going to discuss about functions and see how we can plot functions given various aspects of a given function before we go to the actually differentiation. So first we are going to discuss about graphs. First we will discuss about graphs. So suppose I have a function, or rather an equation, x plus y is equals to 7. I have the function 3x plus y is equals to 7. You realize the point 2, 1 is actually a solution point to the equation 3x plus y is equals to 7. And how is that? Because when I substitute the value of x and the value of y to the equation, I'm getting 7. I'm getting the solution as 7. That is, if I take 3, I substitute x as 2 plus y, that is 1. Here I'm getting the answer to be 7. So of course, the point 2, 1 is a solution point to the equation 3x plus y is equals to 7. Also, the points 1, 4 and the points 0, 7 are also solution points to the equation 3x plus y is equals to 7, because when I substitute the value of x and the values of y, I'm getting the solution as 7. So these points are also solution points to the function 3x plus y is equals to 7. So the set of solution points defines the graph of that equation. So this set of solution points, that is 1, 4, 0, 7, and also the point 2, 1, defines the graph of this equation 3x plus y is equals to 7, such that whenever we want to draw the graph of the equation 3x plus y is equals to 7, we'll be using this set of the solution points to come up in order to come up with the graph of this given equation. And we realize the graph of any equation in two variable x and y drawn on two-dimensional plane gives us a pictorial, hence a geometrical behavior of a given equation. So if we have an equation like 3x plus y is equals to 7, and we plot the solution points of this particular equation, we will get to see and to know the geometrical behavior of this particular equation. Also, the graph can be achieved by actually doing what we call sketching. That is, if certain graph parameters are given. So in this tutorial, we are going to see how we can plot a graph of an equation using the solution points, and also see how we can sketch the graph of an equation using certain graph parameters that will be given. So let's have an example. Example 1. Let's have an example and call this example 1. Suppose we have the function y is equals to x squared minus 2. We have the function y is equals to x squared minus 2, and we want to come up with the graph of this equation. How do we come up with the graph of this equation? Using the solution points. So you realize we can have some solution here, and under the solution, step number 1 is to construct a table of values. So step number 1 is to construct a table of values, a table of values. That is step number 1. And this table of values will be the values of the solution points, will be the values of the solution points. Step number 2 is to plot. Step number 2 is to plot the points, to plot the points of the constructed table, of the constructed table on a two-dimensional plane, on a two-dimensional plane. So after obtaining the solution points from the constructed table, we will plot the points on a two-dimensional plane, on a two-dimensional plane. And step number 3, we will connect. We will connect. So connect the points. Connect the points with a smooth curve. 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 That will be the last step in order to come up with the graph of this particular equation. So let's go to step number 1, constructing the table of values. So I have the x values and the y values like that. So suppose I set x to be -2, x to be -1, x to be 0, x to be 1, and x to be 2. What are the corresponding y values based on the equation? What are the corresponding y values based on the equation? You realize if I substitute here -2, -2 squared will be 4 minus 2, that is 2. -1 squared, that is 1 minus 2, this will be -1. And here it is 0 minus 2, this will be -2. And here is 1 minus 2, that will be -1. And here I'll be having 4 minus 2, this is 2. So these are the solution points from the constructed table of values. These are the solution points. Then I go to step number 2, where I plot the points on of the constructed table on a two-dimensional plane. So I need to come up with a two-dimensional plane. And this is my plane. I'm having my y-axis like that. And here I'll be having my x-axis like that. My x-axis. So this I can say it is 1, 2, 3, 4, 5, 6. So 2, 4, 6, -1, -2, -3, -4, -5, -6. So -2, -4, -6. I can say 1, 2, 3, 4. So this is 2, this is 4. Can say -1, -2, -3, -4. So this is -2 and -4. So at x is -2, y is 2. At x is -2, y is 2. I have that point there. At x is -1 here, y is -1. So at x is -1, y is -1 somewhere there. At x is 0, y is -2. At x is 0, y is -2 somewhere there. And at x is 1, y is -1. At x is 1, y is -1 somewhere there. And at 2, x is 2, y is 2. At x is 2, y is 2 somewhere there. So then I go to the last step, that is connecting the points with a smooth curve. So I'm connecting these points with a smooth curve. I'm connecting these points with a smooth curve. Let me connect these 2 points using a smooth curve. I hope to use a finer pen, but we'll just do it with this. We are connecting with a smooth curve. We are connecting with a smooth curve. Though my curve is not that smooth here, but at least we have tried. So this is how we can construct the graph using the solution points, and these are the solution points. So this is the graph of y is equals to x squared minus 2. All you need to have is to construct a table of values and these values are actually the solution points of the equation, and you plot the solution points. Now you realize one disadvantage of point plotting is that to get a good idea of the behavior or about the shape of the curve, you need to plot as many points as possible. You need to plot as many points as possible, and this is because using the first few points can lead to misinterpretation of the behavior of the graph. Using first few points can lead to misinterpretation of the behavior of the graph. Like for instance, at this point, we are not sure as either the curve is moving upwards or either the curve is moving downwards and such. So to get a clear understanding of this curve, we will have to have as much points as possible. Now, other than point plotting, the graph can, of a given equation like this one, can be obtained by using intercept and symmetric properties. The graph of this function, the graph of a function like this one here, can be obtained by using the symmetric properties and the intercept properties. Once we know the intercepts and the symmetric properties, then we will be good to go to sketch the graph. And you realize the beauty of knowing the intercepts and the symmetric property is that we will actually need few points. We will actually need few points as compared to point plotting. So with that, let's go ahead and discuss about intercept of a graph. So let's go ahead and discuss about intercept of a graph. We will be discussing about, sorry for that, but I need you guys to see this. Intercept of a graph. Intercept of a graph. Basically, an intercept of a graph is the point where the graph is cutting either the x-axis or the y-axis. So we know that the point A, 0 and the point 0, B are actually the x-intercept and the y-intercept respectively. The points A, 0 and the point 0, B are the x-intercept and the y-intercept respectively. And how is that? These are the points at which the graph cuts the x-axis and the y-axis respectively. Because we know the graph will cut the x-axis at some value A, but the value of y will always be 0 at the x-intercept. And we also know that the graph will cut the y-axis at some value B, but the x value will always be 0. And that is why we are saying the point A, 0 and the point 0, B are the x-intercept and the y-intercept respectively. And since we have not much to discuss about the intercept of a graph, we will go ahead and have an example and see how we can determine the intercepts. We can call this example 2. We can call this example 2. So suppose we have a function y is equals to x cubed minus 4x. Y is equals to 4 cubed minus 4x. And we are told to find the intercept of the graph. Find the intercept of the graph. Find the intercept of the graph of this particular equation. How are we going to do that? So let's write some solution. And we'll start calculating, or rather finding the x-intercept. And we know to find the x-intercept, we set the y value equals to 0, because always when the curve cuts the x-axis, the y value will always be equal to 0. So to get the x value, we will now substitute the y value to the mother function, to the function. So that is from y is equals to x cubed minus 4x. Substituting y with 0, this will imply that 0 is equals to x cubed minus 4x. We can go ahead and factor out x here. So we will be having 0 is equals to x. Factor out x here, we'll be having x squared minus 4. So this implies that x is equals to 0, and it also implies that x squared minus 4 is equals to 0, because these two are actually connected by multiplication. So this one will imply that x squared is equals to 4, and therefore x is equals to 2 or negative 2. So we're having some solution of x here and here. So it implies that x is equals to 0, x is equals to 2, and x is equals to negative 2, and x is equals to negative 2. So thus the points, we want to write this in point form, in a coordinate form, because actually the x-intercept is given in coordinate form. So the point will be 0, 0. The point will be 0, 0, because the x value is 0, and of course the y value is 0 here, and the other point is 2, 0, and the final point will be negative 2, 0. So these are the x-intercept of the function y is equals to x cubed minus 4x, of the function y is equals to x cubed minus 4x. So let's go and do for the y-intercept. How do we get for the y-intercept? For y-intercept, here now we set x is equals to 0. We set x is equals to 0. So to the mother equation, from the function y is equals to x cubed minus 4x, we substitute in the value of x as 0, and this will imply that y is equals to 0 cubed minus 4 into 0, implying that my y is equals to 0. And thus, the point will be 0 for the x value, 0 for the y value, and this is the y-intercept. This will be the y-intercept. So I have my y-intercept and my x-intercept. So basically, that is all about intercepts. And now we are going to discuss about the symmetry. So symmetry of a graph. Knowing the symmetry of a graph before attempting to sketch it is basically very useful, because we will need only have as many points to sketch the graph. Unlike in point plotting, where we need several points in order to come up with the graph, knowing the symmetry of a graph will try to simplify in sketching the graph. Actually, we'll need half as many points in sketching the graph. And basically, there are three types of symmetry. Number one, symmetry or symmetry with respect to the y-axis. Symmetry with respect to the y-axis. So let's say symmetric. Symmetric with respect to the y-axis. Symmetric with respect to the y-axis. And when is a graph said to be symmetric with respect to the y-axis? Actually, a graph is said to be symmetric with respect to the y-axis if whenever we have a point x, y, and this point is a point on the graph, then negative x, y is also a point on the graph, Don't worry, we'll explain this. We are saying a graph is said to be symmetric with respect to the y-axis if whenever x comma y is a point on the graph, then negative x comma y is also a point on the graph. So it means that the portion of the graph to the left of the y-axis is actually a mirror image of the portion to the right of the y-axis. This portion, this coordinate is actually a mirror image of this coordinate. So we will say that it is symmetric with respect to the y-axis. Maybe I can have a sketch, and this will help us understand it even better. So that is my y-axis and this is my x-axis. So my y-axis and this is my x-axis. So we are saying a graph is symmetric with respect to the y-axis if whenever we have a point x comma y, you realize this is the positive x-axis and this is the positive y-axis. So I have a point here, x comma y is a point on that particular graph of a given function. Then the point negative x comma y, you realize this is the negative x-axis and this is the positive y-axis. So negative x comma y will be a point somewhere here. So we are saying whenever we have a point x comma y, there is another point negative x comma y, then that graph will be symmetric with respect to the y-axis. And I was even saying this means that the portion to the left of the y-axis is a mirror image of the portion to the right of the y-axis. So this portion is a mirror image of this. This portion is a mirror image of this portion, and therefore the whole graph is said to be symmetric. The other type of symmetry is symmetric with respect to x-axis. Symmetric with respect to the x-axis. So when is a graph said to be symmetric with respect to the x-axis? Actually, a graph is said to be symmetric with respect to the x-axis if whenever we have a point x comma y is a point on the graph, then we will be having another point. And what is that point? That point will be x comma negative y is also a point on the graph. So a graph is symmetric with respect to the x-axis if whenever x comma y is a point on the graph, then x comma negative y is also a point on the graph. And this means that the portion of the graph below the x-axis is actually a mirror image of the portion. This portion below the x-axis is actually a mirror image of the portion above the x-axis. Maybe we can as well have a graph here and try to understand it even better. This is my y-axis and this is my x-axis. So we are having a point x comma y, the positive x-axis, the positive y-axis. So x comma y, let's say it is a point here. We are also saying we'll be having another point x comma negative y. We know the negative y-axis is here, the positive is here. So x comma negative y will be some point here. And that is why we are saying this means that the portion below the x-axis is actually a mirror image of the portion above the x-axis. And with that, we will say that a function is symmetric with respect to the x-axis. The third type of symmetry is symmetric with respect to the origin. symmetric with respect to the origin. And when do we say a graph is symmetric with respect to the origin? If whenever we have a point x comma y, and this is a point on the graph, then we will be having another point x comma negative x negative y as also a point on the graph, The graph is said to be symmetric with respect to the origin if whenever we have a point x comma y as a point on the graph, then we'll be having another point negative x negative y as also a point on the graph. And this means that the graph remains unchanged by a rotation of 180 degrees about the origin. This graph remains unchanged by a rotation of 180 degrees about the origin. As well, we can have a graph here trying to illustrate that. My y-axis and my x-axis. So we are having a point x comma y. The point x comma y is somewhere here. Negative x negative y is somewhere here. And we are saying that this graph will be symmetric with respect to the origin, and this is the origin. And you realize the point here is actually rotated through an angle of 180 degrees. So the graph remains unchanged through an angle of 180 degrees. And with that, we are done with symmetric. That is, we only have three types of symmetry. That is symmetric with respect to the y-axis, symmetric with respect to the x-axis, symmetric with respect to the origin. That is what we are going to discuss in terms of symmetry as per this tutorial. Now, suppose we are given a function. And given that particular function, we are told to determine if that function is either symmetric with respect to the x-axis, or it is symmetric with respect to the origin, or symmetric with respect to the y-axis. How do we determine the symmetry of a given function or an equation? Or in simple terms, how do we test for symmetry? So with that, we will go ahead and discuss on testing for symmetry. We will go ahead and discuss on testing for symmetry. So, testing for symmetry. Number one. Under testing for symmetry, number one, symmetry with respect to the y-axis. Symmetry with respect to y-axis. How do we test for symmetry with respect to y-axis? You realize we said a graph is symmetric with respect to the y-axis if whenever we have a point x comma y as a point on the graph, then we will be having another point negative x comma y as also a point on that particular graph. So you realize the y value is not changing, but the x value is changing from positive to negative. So to test for symmetry with respect to y-axis, we actually replace, replacing x with the negative x to the original function, and this should yield the same equation. So a function is said, or an equation is said to be symmetric with respect to the y-axis if when we substitute x with negative x will give us the same equation. So number two, testing for symmetry with respect to x-axis. So symmetry symmetry with respect to x-axis. Symmetry with respect to x-axis. So you realize we said a graph is said to be symmetric with respect to x-axis if whenever we have a point x comma y as a point on the graph, then we'll be having another point x comma negative y as also a point on that particular graph. So you realize the x values are not changing this time round, but the y values are changing. So to test for symmetry with respect to the x axis, we actually replace. So replacing the y values or with y. We are replacing the y values with the negative y, and this should yield the same. This should yield the same equation. This should yield the same equation. So the third is symmetry. Symmetry with respect to origin. Symmetry with respect to the origin. Now you realize we said that a graph is symmetric with respect to the origin if whenever we have a point x comma y as a point on the graph, then we'll be having another point negative x negative y as also a point on that particular graph. So this time round, both x values and y values are changing from positive to negative. So to test for symmetry with respect to the origin, actually we replace. So replacing x with negative x and y with negative y, because both are changing, and this should yield the same equation. Should yield the same equation. So basically, that is how we test symmetry. That is how we test symmetry. So example, and we can call this example 3. We can call this example 3. So test for symmetry. Suppose we have a function y is equals to 2x cubed minus x, and we are told to test for symmetry. Test for symmetry with respect to, and Roman 1 we say with respect to the y-axis, Roman 2 with respect to the x-axis, and Roman 3 with respect to the origin. With respect to the origin, we actually know how to test the symmetry, but let's go ahead and do it practically. So I'll be writing some solution. So solution, and we start with Roman 1. So with respect to the y-axis, and we said to test for symmetry with respect to y-axis, what do we do? Replacing x with the negative x in the mother function or in the mother equation. So replacing x with the negative x in the mother equation. So from the mother equation, y is equals to 2x cubed minus x. We are actually replacing x with the negative x. So this implies that we'll be having y is equals to 2 negative x cubed minus x. We are replacing with the negative x. And this will give me y is equals to negative x cubed will be negative x. So minus 2x cubed plus x. Negative x cubed will be negative x cubed, that is. So we are ending up with this function. So I can name this resultant function to be Roman 2 and the mother function to be Roman 1. Now you realize function number 1 or Roman 1 and function Roman 2 are not equal. That is, the resultant equation is not equals to the mother equation. So therefore, there is no symmetry with respect to the x-axis. So we can say since equation 1 is not equals to equation 2, since equation 1 is not equals equation 2, no symmetry, not symmetric with respect to to the y-axis, not symmetric with respect to the y-axis. Then on Roman 2, testing for symmetry with respect to x-axis. Testing for symmetry with respect to x-axis. And we said here we replace, so replacing y with the negative y in the mother function. Replacing y with the negative y in the mother equation. What does this mean? So from the mother equation, y is equals to 2x cubed minus x. So where there is y, we replace it with negative y. So it implies that negative y is equals to 2x cubed minus x. So if we divide through by negative, we will be having y is equals to minus 2x cubed plus x. So if I call this resultant equation as Roman 2 and the mother function as 1, you realize the resultant equation is not equals to the original equation. And since the resultant, the mother function is not equals to the resultant equation, we say the function is not symmetric. The function is not symmetric with respect to the x-axis, with respect to the x-axis. So what is remaining? We remain to test symmetry with respect to the origin. So we are remaining to test symmetry with respect to origin. So let's go to Roman 3 on a new page here, and we try to test for symmetry, and we try to test for symmetry. So let's go to Roman 3. Roman 3 with respect to origin, with respect to the origin, with respect to the origin. So with respect to the origin, we are having our function. So from the function, the function was y is equals to 2x cubed minus x. So with respect to origin, replace. So replacing, we said with respect to origin, when we want to test symmetry, we replace x with negative x and y with negative y. We replace x with negative x and y with negative y. So where there is y, we replace it with negative y. So we'll be having negative y is equals to, where there is x, we replace with the negative x. So 2 into negative x cubed minus x, because this x is replaced with negative x. So this will give us minus y is equals to minus 2x cubed plus x. So when I divide through by a negative, I'll be having negative 1, I'll be having y is equals to, I'm trying to remove this negative here, 2x cubed minus x. So I call the resultant equation as 1 and the original equation as 1, the resultant as 2, sorry. So since the mother function or mother equation is actually equal, sorry, it should be equal, is actually equal to the resultant equation, that is Roman 2, then the equation is symmetric. The equation is symmetric with respect to the origin, with respect to the origin. You realize this function here is actually equal to the mother function there. So because of that, we say that the graph is symmetric with respect to the origin, with respect to the origin. So we have discussed the intercept. We have discussed the intercept. We have also discussed the symmetric property of a function. So having the intercept and the symmetric property, we can go ahead and sketch the function. We can go ahead and sketch the graph of a given equation. So let's have an example here. Let's have an example here. Actually, because it involves sketching, let's have it on a new page. Actually, because it's involving sketching, we can have it on a new page. So I'll call this example as example 4. So example 4, and under example 4, we are having a function x minus y squared is equals to 1. So, and the instruction is using intercept and symmetric property and symmetry, sketch the graph. We are having this function, so we are told to use the intercept and the symmetric property to sketch the graph. So let's write some solution. There. So we know for x-intercept, let's start determining the intercept. So for x-intercept, we know that for x-intercept, to determine this x-intercept, we set our y is equals to 0, because whenever the function, or rather the graph, cuts the x-axis, then the y value will always be 0. So let's get the x value. So this implies that from the original function, x minus y squared is equals to 1, substituting the value of y as 0. So this implies that x minus 0 squared is equals to 1, and my x will be equal to 1. And thus, the point 1, 0 is actually the x-intercept, of the curve, So since we have the x-intercept, there's no need of computing the y-intercept. We can go ahead and determine the symmetry of this function. And since we realize that the function is cutting the x-axis based on the intercept at 1, it is good starting to determine if they is symmetric with respect to the x-axis. It is good to test for symmetry with respect to the x-axis before thinking of y or the origin. We need to think about the symmetry with respect to x-axis, since it is cutting the x-axis based on the intercept. So test for symmetry. And it is about the x-axis. So we are testing for symmetry about the x-axis, and we said when we want to test for symmetry with respect to the x-axis, we actually replacing y with the negative y to the mother function. We are replacing y with the negative y to the mother function. So from the mother function, x minus y squared is equals to 1. I can call this mother function Roman 1. And now we are replacing y with the negative y. So it implies that x minus negative y squared is equals to 1. And this will give me x minus negative y squared is y is equals to 1. So this is the resultant function. Now you realize since the resultant function Roman 2 is equals to the mother function Roman 1, there is, we can say there is symmetry. There is a symmetry with respect to x-axis. There is symmetry with respect to x-axis. Why? Because the resultant equation is equals to the mother equation. The resultant equation is equals to the mother equation. Now that we have the intercept, that is the x-intercept, and we have the symmetric property, we can go ahead and sketch the graph. All we need to have is half points, as in point plotting when we were sketching the graph. So we also know that the points we also know that the points 2, 1 and the point 5, 2 are also solution points, are also solution points to the graph y x minus y squared is equals to 1. X minus y squared is equals to 1. X minus y squared is equals to 1. So 2, 1 and 5, 2 are also solution points to the curve, x minus y squared is equals to 1. So because of that, we can actually go ahead and plot the curve using this property. And here we go. I'm having my y-axis. I'm having my y-axis like that. This is my y-axis. I'm having my x-axis like that. This is my x-axis. So I'll be having, let's say this is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Just a matter of sketching. 1, 2, 3, 4. 1, 2, 3, 4. Like that. So this is 2, 4, 6, 8. This is 2 and this is 4. This is negative 2 and this is negative 4. Negative 2, negative 4 and negative 6, like that. So for the x-intercept, it is 1, 0. So 1 here, 0. So this is my x-intercept. This is my x-intercept. That is 1, 0. For the x-intercept, it is 1, 0. Then for the other solution points, I know it is 2, 1. 2, 1 here is a solution point 2, 1. Then another solution point is 5, 2. So 5, 2 is also a solution point. Now, you realize we have just tested for symmetry about the x-axis, and we have actually concluded that there is symmetry with respect to the x-axis. So because there is symmetry with respect to the x-axis, and we know that whenever we have a symmetry with respect to the x-axis, the x values are not changing, but the y values are assuming a negative. So it means that if I have a point 2, 1, then there is another point 2, negative 1 here is also a point on the graph. That is what we were just saying in symmetry. And since I have a point 5, 2, then I'll be having another point 5, negative 2 here as also a point on that particular graph. That is why we were saying we only need half of the points to sketch the graph. We didn't need to know these solution points. We only needed this and the symmetric property in order to generate the rest of the points. Now with that, we can join the points using a smooth curve. We can join the points using a smooth curve. And since under symmetry we said the portion of the graph below the x-axis is actually a mirror image of the portion of the graph above the x-axis, the portion below the x-axis will be assuming dotted line. The curve will be over dotted line to show that this portion is actually a mirror image of the portion above the x-axis. So we are saying the portion of the graph below the x-axis is a mirror image of the portion of the graph above the x-axis, since there is symmetry with respect to the x-axis. Is the symmetry with respect to the x-axis. So that is all about graphs. We have discussed how we can sketch the graph of a given equation using the point plotting, where we were actually obtaining a set of solution points and come up with the graph. we have also seen how we can use the intercept and the symmetric property to come up with a graph as the one we are having here. So with that, we are come to end with the graphs under differentiation. In the next tutorial, we are actually going to introduce about functions. We are going to talk about functions. So in the next tutorial, as we'll be covering functions, we are actually going to talk about definition. That is a definition of a function. What is a function and all that. We will also go and discuss about the domain and the range of a function. The domain and the range of a function. Having discussed the domain and the range of a function, we will go ahead and discuss about classification and combination of function. That is classification and combination of function and combination of functions and combination of functions. We'll also go ahead and discuss about even and odd function. Even and odd function. That is when a function is said to be odd and when a function is said to be even. We will also go ahead and discuss about the inverse of a function. We'll discuss about the inverse of a function. We will also discuss about composition of a function. Composition of a function or composition of functions. So we suppose we have two functions. How can we form one function based on the two given set of functions? So all you need to do is to subscribe, click the notification bell, and wait for the best tutorial. Kindly subscribe, share, like, and comment. Let's meet on the next tutorial. All the best.